In ancient Greek mythology, the labyrinth was an extremely complex maze built to contain the fearsome Minotaur. Legend has it that Daedalus, its architect, could hardly escape it himself once it was built. For our final challenge in RSS, we put our robot in the Minotaur's shoes. We were tasked with programming our robot to escape from a starting point within a labyrinth under several conditions. The robot is not allowed any prior knowledge of the labyrinth. The labyrinth is not simply connected, meaning it may have islands, and the labyrinth is multicursal, meaning there are multiple paths to the exit. This challenge emulates an important problem in modern robotics. Robots often require a map in order to navigate their environment. However, there are many cases when there are no maps available. This is very common in robotic exploration, especially extraterrestrial or subterranean domains, for example, where GPS is out of the question and existing maps are few and far between. So going back to the challenge, how do we make it work? SLAM stands for simultaneous localization and mapping. It is a technique that is greatly useful in navigating unknown environments. For this challenge, we use Google Cartographer, a program that carries out SLAM by taking in sensor data to build a single cohesive map over time. We also need an efficient way to explore it to continue building the map. Our proposed method is frontier-based exploration. We find frontiers by examining our current map and looking for where known occupied regions meet unknown regions. These are called boundary pixels. Next, we look for clusters of boundary pixels called frontier regions. The more boundary pixels are present in an area, the more information the robot can gain by exploring that area. Once the frontier regions are determined, the robot performs a breadth-first search to find the closest one. This is our chosen frontier. Now we need to get there. We have a variety of path planning algorithms under our belt from previous labs. For this challenge, we propose using RRT star, Rapidly Exploring Random Tree, which is an algorithm that builds a tree of paths via random sampling until it reaches the goal. To follow the built path, we propose using a pure pursuit controller, which we developed in a previous lab. Pure pursuit works by setting a goal point on the path a fixed distance away from the robot and constantly driving towards that point. Though all these components worked individually, we encountered issues in the integration of our path planning with our path following. To save ourselves the headache of debugging an increasingly complex and entangled system, we opted for a simpler approach, an alternating wall follower. The wall follower works by running a linear regression on the robot's laser scan data to estimate the position of the wall to the robot's side. The red line here indicates the estimated wall position. The robot then drives parallel to the wall at a fixed distance. If it's too close to the wall, it steers away, and if it's too far, it steers closer. We also command the robot to back up when it detects an imminent collision with the wall. The problem with the standard wall follower in this scenario is that it will endlessly drive around islands. This is why we chose an alternating wall follower. This simply means that at a fixed time interval, the robot will switch from following the wall on its right to following the wall on its left, or vice versa. This gives the robot the ability to explore and escape the maze without getting stuck. On demo day, our controller performed wonderfully. Though it's not as intelligent as our initially proposed approach, it still explores and maps the environment efficiently, and it escaped the maze with much time to spare. And at the end of the day, that's all that mattered.
All right, yeah.